Miles of rock separate us from the heart of our planet. What's really hidden beneath our feet? How has the Earth shaped its bowels over billions of years? In 2024, while we may have mapped every nook and cranny of the Earth's surface, the center of our planet remains one of science's greatest mysteries. A hostile and fascinating world where temperatures reach those of the sun's surface and where the pressure is so intense that it transforms matter itself. Dear traveler, welcome. Today we're off on a dizzying journey, a descent into the depths through the different layers of the Earth, from the thin crust we're walking on to the molten core. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thanks, and have a great trip! Exploring the Earth's interior has always fascinated scientists and the curious. Yet despite decades of effort, man has never managed to dig deeper than 12 kilometers or 8 miles below the surface. This ambitious project aimed to drill as deep as possible to reach the deep layers of the Earth's mantle. However, after reaching 12 kilometers or 8 miles, the researchers had to stop because the extreme temperatures and pressures made the operation increasingly difficult and dangerous. At these depths, the heat was already reaching over 200 degrees Celsius, or 392 degrees Fahrenheit, endangering the equipment. It's not just the heat that's a problem, but also the pressure, which becomes thousands of times greater than at the surface. This phenomenon makes exploration of these depths technically impossible with current technologies. But what is there in the depths of the Earth that we haven't yet been able to explore? Scientists have come up with several fascinating hypotheses. Many believe that beneath the Earth's crust lies a mantle of semi-molten material and dense rock, but what lies below in the core remains something of a mystery. Some suggest that geothermal phenomena, convection currents, or even microscopic life forms could exist at these extreme depths. It's also possible that materials we don't yet know about are present, which could offer revelations about the origins of the Earth and our solar system. Although difficult to access, these hypotheses continue to fuel scientific curiosity and research into our planet's interior. Since ancient times, notably with Aristotle, many scientists and thinkers have speculated on the nature and composition of the Earth. Early reflections dating back to the 7th century BC involved Greek philosophers such as Thales, Anaximander, Pythagoras, Plato, and Aristotle, who saw the Earth as a stable sphere at the center of an equally spherical universe. Aristotle describes the Earth as consisting mainly of the element Earth, surrounded by water, air, and a layer of fire. He also imagines the presence of internal cavities in the globe, explaining that phenomena such as earthquakes and volcanoes are caused by the escape of internal forces, such as wind from these cavities. With Copernicus's astronomical revolution, old conceptions of the Earth were abandoned in favor of new ideas. In 1644, René Descartes proposed a vision of the Earth as a hollow body, formerly the Sun, with a core of solar matter surrounded by different layers. Dense Earth, water, air, and a layer of light Earth above a void. According to him, the Earth's internal structure was formed through a cataclysmic collapse, which also gave rise to the oceans. Athanasius Kircher, in 1665, presented a different picture. While viewing the Earth as an ancient, cooled sun, he emphasized its intense internal activity. According to him, a restless central focus is connected to volcanoes on the surface by conduits of fire, with volcanoes representing outlets for this internal energy. After Descartes and Kircher, conceptions of the underground world rapidly diversified, largely to explain the formation of the Earth in the biblical flood. In 1681, the theologian Burnet proposed that the Earth, originally a fluid chaos, was structured by gravity, with heavy elements gathering at the center and light elements rising to the surface. According to him, the Earth is layered, with a central core of fire, and the flood would have resulted from a collapse of the outer layer, thus shaping the Earth's surface. For his part, Woodward, a naturalist, focused on the superposition of geological layers. In 1695, he suggested that the rocks of the flood had been dissolved and redeposited in concentric layers by gravity. His vision of the Earth involved an inner sphere of water, communicating with the oceans through openings. In 1696, Whiston proposed that the Earth was an ancient comet, with a solid hot core, a dense fluid layer, and a crust balanced on this layer, with relief resulting from differences in density. He links the flood to a new comet bringing water vapor, causing torrential rains and tidal cracks in the crust, leading to the eruption of internal waters. Once the comet has moved away, the water from the flood evaporates, returns to the depths, or forms the seas, giving the Earth its present appearance. In 1693, Halley, an astronomer and contemporary of Newton, put forward the idea that the Earth is hollow, with a freely floating magnetized core, to explain variations in the magnetic field. He even imagined that the Earth consisted of 3 arches with a rotating core, whose dimensions resembled those of the radii of Mercury, Mars, and Venus. These arches function thanks to the magnetic force that counterbalances gravitation, and could be inhabited, separated by rarefied spaces. In 1721, the engineer Gautier proposed a theory according to which the Earth would be entirely hollow, resembling a balloon, with an outer crust less than 5 kilometers or 3 miles thick. This crust would be held in balance by gravity and the Earth's rotational force, creating a symmetry that would allow the existence of an inner world with its own relief. Gautier used this theory to explain the lifting and collapsing of the crust, which was not possible with the idea of a solid Earth. In 1740, Ab Moro, observing the recent formation of an island near Santorini, put forward the hypothesis that all terrestrial landforms are of volcanic origin. He suggested that crustal uplift could create internal cavities, either filled with volcanic material or shaped by a deformable igneous core. In the 18th century, several representations of the subterranean world emerged, but their veracity was called into question. Buffon, in 1749 and 1778, sought to establish a theory of the Earth based on solid evidence. He argues that the Earth is solid, based on the orientation of a plumb line near the mountains. In addition, he puts forward 3 arguments to demonstrate that the Earth was entirely molten in its early days: the Earth's flattened shape, the high temperatures observed in mines, and the composition of mountainous rocks, characteristic of prior melting. In the early 19th century, geology emerged as a scientific discipline, ending the dominance of philosophical and theological perspectives on the Earth. The geologist Cordier, building on Fourier's work, observed in 1827 that the temperature in mines increased by 1 degree for every 25 meters of depth. He suggested a temperature reaching 1600 degrees Celsius at a depth of 50 kilometers, or 2900 degrees Fahrenheit at 30 miles, which would indicate a molten landmass beneath a thin solid crust. This hypothesis explains geological phenomena such as volcanoes and earthquakes. However, discordant voices such as those of Davy, Ampere, Poisson, and Lyell criticize this theory. They believed that the Earth's heat could come not from original fusion, but from exothermic thermal reactions. Hopkins pointed out that the melting temperature of rocks depends on pressure, challenging Cordier's assertions and suggesting that experimental research is needed to understand the state of internal rocks. In 1862, Lord Kelvin maintained that the Earth was entirely solid, arguing that if it were molten, strong internal tides would deform the ground, something that had not been observed. Although he finds that ocean tides are slightly lower than predicted, this indicates that the Earth acts as an elastic solid similar to steel. Thus, he concludes that only the magma beneath volcanoes is liquid, firmly opposing the fluid model proposed by other geologists. In the 1870s to 80s, the debate over the Earth's internal structure was intense. Fisher proposed a three-layer model: a solid crust, a fluid intermediate layer, and a solid core, which met Lord Kelvin's criteria while explaining geological phenomena. Roche, in 1881, presented a two-layer model with a dense iron core covered by a stony layer. Meanwhile, in 1878, Ritter proposed the idea of a gas core, supported by observations of the Earth's internal temperatures. Gunther extended this theory in 1884, suggesting a model with a solid crust, a molten layer, and a gas core, whose popularity increased with Arrhenius' support in 1900. However, these ideas were gradually superseded by advances in seismology. Seismological auscultation, which began in the 20th century, has profoundly altered our understanding of the Earth's structure. The detection of shear S waves, which do not travel in liquids, revealed that the upper part of the Earth behaves like an elastic solid. This observation prompted geologists to revise their theories on volcanoes and mountain formation. Oldham in 1906 created the first seismological model of the Earth and noted that S waves show a significant delay for epicentral distances above 130 degrees Celsius or 266 degrees Fahrenheit. He attributed this phenomenon to a central zone where wave velocity is lower, suggesting a major seismological discontinuity around 3,800 kilometers or 2,360 miles in depth. In 1909, Mohorovic observed an increase in seismic velocities beneath Croatia at 54 kilometers or 33 miles depth, interpreted as the boundary between crust and mantle. In 1912, Gutenberg adjusted the depth of the Oldham discontinuity to 2,900 kilometers or 1,800 miles, a value still accepted today. He also noted that P waves emitted by earthquakes are normally recorded up to 105 degrees angular distance from the epicenter of an earthquake. Between 105 degrees and 142 degrees from the epicenter, P waves are not detected, a phenomenon known as the seismic shadow zone, which Gutenberg attributes to a discontinuity in wave velocity. In the early 20th century, most seismologists believed that the Earth's core was solid. However, in 1926, Jeffreys demonstrated that the core was in fact fluid, based on the rigidity of the materials and not on the absence of S waves. This theory was quickly accepted by the scientific community. In 1936, Danish seismologist Inge Lehmann discovered that the liquid core had a solid core, which she called a seed. She explained the reappearance of P waves in the shadow zone by their scattering at the boundary of this solid core. Her conclusions were validated by the work of Gutenberg in 1938 and Jeffreys in 1939, who estimated the dimensions of the seed at between 1,200 and 1,250 kilometers, or between 745 and 776 miles, a measurement confirmed today at 1,221 kilometers or 758 miles. In 1940, Birch suggested that the Earth's seed was solid, an assertion that would not be confirmed until 1960, thanks to the analysis of the Earth's own oscillations, enabling recognition of the great internal structures of the Earth known today. When the Earth was formed some 4.5 billion years ago, it was far from being the stable, layered planet we know today. In its early days, the Earth was a hot sphere, composed almost entirely of molten rock. During this period, material from outer space accumulated under the influence of gravity, generating intense heat. This heat caused the partial melting of terrestrial materials, separating them according to their density. Metal, mainly iron and nickel, being denser, migrated to the center of the planet to form the core, while the lighter rocks remained on the surface. This primitive world was nothing more than an ocean of magma, where extreme conditions of heat and pressure were omnipresent. Over time, however, complex processes shaped the planet's interior, creating a layered structure that continues to play a fundamental role in its functioning today. Around 500 million years after the Earth's formation, the planet's internal temperature reached a critical threshold, that of iron fusion, at around 1,538 degrees Celsius, or 2,800 degrees Fahrenheit. This event, known as the Iron Catastrophe, marked a major turning point in the Earth's geological history. During this catastrophe, the intense heat allowed heavy metallic elements, such as iron and nickel, to liquefy and move more easily under the influence of gravity. The molten iron droplets slowly sank towards the center of the planet, forming the Earth's metallic core. The Earth's core is divided into two parts, the outer core, which is liquid, and the inner core, which is solid. This distinction is explained by variations in pressure and temperature at different depths, which influence the physical state of the materials. Above the core is the mantle, a layer composed mainly of silicates. The mantle is subdivided into several zones due to phase transitions that alter the atomic arrangement of minerals, giving them distinct properties. This process of separating materials according to their density has been decisive in the internal organization of the planet. Lighter matter, composed of silicates and other less dense elements, was expelled to the exterior of the Earth, where it formed what we know today as the Earth's crust. This phenomenon is known as planetary differentiation and is essential to understanding the distribution of the Earth's different layers. The inner core, rich in iron and nickel, became the heart of the Earth, while the mantle, made up of lighter rocks, grew up around it. Once planetary differentiation had taken place, the Earth continued to evolve. Surrounding the forming core was the primitive mantle, a mixture of molten rocks. This mantle gradually began to solidify as the internal temperature dropped. At the same time, so-called incompatible elements such as lighter gases and minerals migrated outwards, forming the Earth's crust. The Earth's crust, located at the top, is made up of different rock types from those in the mantle. It is formed mainly by volcanism, when magma from the mantle rises to the surface, cools and solidifies to form lighter rocks. These less dense rocks float to the surface, creating a distinct layer. This crust, relatively fragile and thin compared to the other layers, was the first to solidify completely, giving the Earth a solid surface. As it solidified, the Earth's crust continued to evolve. But this fragile crust is far from stable. It is constantly changing as a result of plate tectonics, a geological process that continues to reshape the Earth's surface. This movement of tectonic plates generates phenomena such as volcanoes, earthquakes, and mountain building, all of which contribute to the planet's geological dynamics. Another key event in the Earth's evolution was outgassing. As the Earth's mantle solidified, many gases dissolved in minerals were expelled to the surface, a phenomenon that played a crucial role in the formation of the Earth's atmosphere. This outgassing released gases such as water vapor, carbon dioxide, and other volatile compounds, creating a primitive atmosphere. The water contained in the minerals was released in the form of water vapor, which condensed to form the first oceans. This outgassing process not only contributed to the formation of the atmosphere, but also played an essential role in cooling the Earth and creating the conditions favorable to life. As the Earth cooled, liquid water accumulated on the surface, creating oceans, lakes, and rivers, and providing the elements necessary for the emergence of life. The subdivisions of the Earth, whether crust, mantle, or core, reflect both differences in chemical composition and the internal dynamic processes, such as phase transitions that shape our planet's structure. The constantly evolving Earth remains a fascinating example of how internal forces shape the planet as we know it today. The Earth's crust is easily accessible, and this is where scientists can literally dig to understand its composition. Using samples taken from mines and boreholes, they have been able to identify rocks such as granite, basalt, and other minerals. However, this crust is only a fragment of what lies beneath. The challenge of exploring the depths of the Earth has motivated many explorers. In the early 1960s, for example, a project was launched to drill into the Earth's crust, known as Project Mohole. The name comes from the Mohorovičić discontinuity, or MOHO, which marks the boundary between the Earth's crust and mantle. This layer is named after the Croatian meteorologist Andreja Mohorovičić, who discovered it. The Mohole project was the deepest offshore drilling attempt to date. In the initial phase of the project, 5 holes were drilled into the ocean floor at a depth of 3,600 meters or 12,000 feet. Although the project did not progress to the next stage, during which even deeper drilling was envisaged, scientists gained valuable insights into deep-sea drilling techniques. Geologists the world over set out to drill at unprecedented depths. In 1970, Soviet geologists began to work on the Kola Peninsula, not far from Finland, with the aim of drilling deeper into the Earth than anyone had done before. The project, known as the Kola Super Deep Borehole, involved digging a vertical shaft deep underground. The deepest borehole reached 12,262 meters, or 40,230 feet, and was completed in 1989. This borehole is now recognized as the deepest artificial point on the planet. At the maximum depth reached, geologists found that the Earth's crust was hotter than expected, with a temperature of 212 degrees Celsius, or 413 degrees Fahrenheit, against the 100 degrees Celsius, or 212 degrees Fahrenheit expected. The rock then began to become viscous, forcing the team to halt the project. In 2022, ADNOC, Abu Dhabi's national oil company, reached a new milestone by setting a record for drilling the longest oil and gas well. The well, located in the Upper Zakum oil field, measures 15,240 meters, or 50,000 feet deep, surpassing the previous record of 15,000 meters, or 49,200 feet, achieved in 2017 by a well located off the Russian coast. At the same time, another depth record is being attempted by another company in the energy sector. Quaise Energy, founded in 2020, is developing a drilling system to convert existing power plants to use ultra-deep geothermal energy. The company plans to use waves of intense energy to melt rock, with the aim of reaching depths of up to 20 kilometers or 12 miles below the Earth's surface, to reach temperatures in excess of 500 degrees Celsius or 932 degrees Fahrenheit. Drilling is carried out using millimeter-wave directed energy beams capable of vaporizing even the hardest rock. It focuses a high-power beam of radiation similar to microwaves, but with a higher frequency, on an area of rock, bringing it to temperatures of up to 3,000 degrees Celsius, or 5,400 degrees Fahrenheit, to melt and vaporize it. By directing this beam appropriately, it is possible to create wells without the debris and friction associated with traditional drilling methods. Quay's energy is now in the final stages of laboratory testing of millimeter wave technology before beginning field trials in early 2025. However, the transition of millimeter wave drilling technology from the laboratory to a full-scale drilling operation remains a challenging issue. To go further, more sophisticated methods are needed. Scientists can't drill into the mantle or core because the temperatures and pressures there are extreme. So how do they do it? They analyze the seismic waves generated by earthquakes. These waves propagate differently depending on the type of material they pass through, allowing them to scan the interior of the planet. They also measure the Earth's gravity and the influence of the magnetic field, produced in part by the movements of the liquid outer core. These indices enable us to model what's happening beneath our feet with impressive precision. Let's explore these methods in detail. One method of discovering the Earth's internal structure is deployed in the laboratory through experiments and analysis of terrestrial rocks and minerals. The Earth's crust, although thin on a planetary scale, is a veritable geological library. Where it has been disturbed by natural processes such as erosion, or by human activities such as excavation and drilling, distinct layers of rock and sediment can be observed. These layers tell the story of the Earth over millions of years. The appearance and characteristics of our planet, just like those of a living being, are greatly influenced by what goes on deep down. These internal processes, taking place hundreds of kilometers below the surface, shape the Earth in many ways. However, exploring these depths is an immense challenge, as the materials that make up the Earth are both dense and opaque, making direct access very limited. To understand what lies hidden in the bowels of our planet, scientists rely on rare samples from exceptional locations. For example, in a kimberlite pipe in Lesotho, South Africa, rocks brought to the surface reveal information about areas some 250 kilometers or 155 miles below the surface. These volcanic vents act as natural windows into the Earth's depths. To understand the composition of the Earth's crust, geologists collect rock cores, cylinders extracted from the depths. These cores, along with finer debris known as cuttings, are carefully cataloged and preserved. The United States Geological Survey's Center for Basic Research, for example, has spent over 40 years building up a huge repository of these samples. Why keep them for so long? Because technological advances enable ever more precise analyses. In the laboratory, scientists use modern techniques such as mass spectrometry to analyze the chemical composition of samples. Each rock tells a story about its iron and magnesium content, which may indicate its deep-seated origin, while traces of oxides or microscopic fossils reveal geological processes at the surface. But the research doesn't stop there. To go even further, scientists are recreating the extreme conditions that prevail beneath the Earth's crust in the laboratory. Using hydraulic presses capable of exerting pressures of several gigapascals, combined with temperatures reaching several thousand degrees Celsius, they can observe how rocks and minerals behave in the depths. But Earth samples aren't always enough. Meteorites play a key role in our understanding of the planet's interior. These rocky fragments, which often come from asteroids or even disintegrated planets, contain clues to the formation of our solar system. By analyzing their composition, scientists discover striking parallels with deep-seated terrestrial rocks, helping to reconstruct our planet's origins. Thanks to these combined methods, such as field analysis, laboratory experiments, and extraterrestrial studies, scientists are broadening our understanding of the Earth every day. But what's going on deeper down, where physical tools can't reach? Find out now with the study of seismic waves and gravity. Digging to the center of the Earth is simply impossible. With temperatures reaching over 6,000 degrees Celsius or 10,800 degrees Fahrenheit, and pressures unimaginable, even our most advanced drills couldn't manage it. So how do we find out what's going on in those inaccessible depths? The answer lies in the study of seismic waves, the vibrations generated by the earthquakes that crisscross our planet. As they pass through the different layers of the Earth, these waves change speed, bend, or reflect, revealing the composition and state of the materials they pass through. When an earthquake occurs, it generates seismic waves that travel through the Earth. These waves, like X-rays for a doctor, allow us to scan the inner layers of our planet. But that's not all. The speed of seismic waves depends on the materials they pass through. What's more, their direction changes when they encounter a layer of different composition. Seismic waves fall into two main categories. Firstly, P waves, or pressure waves, are the fastest. They can travel through solids and liquids, making them universal messengers. Secondly, S waves, or shear waves, are slower and can only pass through solids. If an S wave disappears, this indicates that it has encountered a liquid, such as the Earth's outer core. Scientists use seismometers, ultra-sensitive instruments that record the slightest movement of the ground. By measuring the time it takes for P and S waves to reach a seismometer, as well as the speed differences between them, they can deduce the composition and state of the layers traversed. For example, a slowing or disappearance of S waves indicates a liquid zone, while variations in P waves suggest changes in density or rigidity. The first major advances thanks to seismic studies date back to 1906. Scientists discovered that the Earth's outer core is liquid thanks to the inability of S waves to penetrate it. The inner core, on the other hand, is solid, confirmed by variations in the speed and direction of P waves. These discoveries are not just a technical feat. They also explain phenomena essential to our life on Earth, such as the creation of the Earth's magnetic field. But scientists have identified another way of learning about the Earth's internal structure. We can't see or touch the Earth's core, but invisible forces like magnetism and gravity help us to unravel its mysteries. These phenomena, though ubiquitous, hide secrets about the composition and structure of our planet. The Earth is enveloped by a powerful magnetic field, sometimes called the Magnetosphere, which acts as a shield against the solar wind. In reality, the Earth's magnetic field is constantly changing. These variations, sometimes subtle, sometimes spectacular, tell us a great deal about the deep dynamics of our planet. One of the most fascinating manifestations of these changes is the inversion of the magnetic poles, a phenomenon in which magnetic north and south exchange positions. These reversals occur irregularly, sometimes after hundreds of thousands of years. During these periods, the magnetic field can weaken, temporarily exposing the Earth to more intense radiation. This field is generated by movements within the Earth's core, But how did scientists discover this? At first, they dismissed the hypothesis of a permanent magnet at the center of the Earth, as temperatures there exceed 1,000 degrees Celsius, or 1,800 degrees Fahrenheit, well beyond the point at which a permanent magnet can operate. The only logical explanation is a phenomenon called dynamo. Ionized molecules in motion in a conductive liquid, such as molten iron, generate this magnetic field. This is direct evidence that the Earth's outer core is liquid and rich in conductive metals. Progressive shifts in the north magnetic pole have also been observed. For example, since the beginning of the 20th century, the north magnetic pole has shifted significantly, traveling across the Arctic. In addition, sudden magnetic tremors, although less frequent, can also occur, revealing disturbances in the outer core. By studying these variations, scientists are indirectly exploring the turbulent movements of the fluid outer core, where the electric currents responsible for the magnetic field are generated. Let's move on to another equally essential force: gravity. Isaac Newton was the first to formulate the theory of the universal force, which was later used to calculate the Earth's mass. Gravity is directly dependent on material density. But that's not all. Scientists have discovered that the Earth's average density is 5 grams per cubic centimeter, while that of the rocks in the Earth's crust is just 3 grams per cubic centimeter. This discrepancy led to the astonishing conclusion that the Earth's interior must be made up of much denser materials such as metals. By comparison, rocks have a density of 3 grams per cubic centimeter, while metals such as iron and nickel have a density of up to 13 grams per cubic centimeter. It's this high density that partly explains our planet's weight and gravitational pull. By combining magnetic and gravitational evidence, scientists have been able to build up a precise picture of the Earth's core. The liquid outer core contains mainly molten iron and nickel. These moving metals generate the Earth's magnetic field. The inner core, on the other hand, is solid, probably made of pure iron or an alloy of iron and nickel, and subjected to such intense pressure that it remains solid despite the extreme heat. Geothermal studies, which analyze the flow of heat from the Earth's interior, play an essential role in our understanding of the planet's inner workings. This heat flow, measured through boreholes or at the surface, results from the dissipation of energy generated by the radioactive decay of elements in the mantle and core, as well as residual heat dating from the Earth's formation. By measuring temperature variations between the Earth's interior and its surface, scientists determine temperature gradients. These gradients reveal how heat flows through the Earth's different layers. For example, abnormally high heat flows in certain regions suggest intense geothermal activity or major movements of material in the mantle. Geothermal energy provides valuable information about the Earth's core, even though it is not directly accessible. Heat from the fluid outer core is crucial for maintaining convection in the mantle, and variations in heat flow across the core mantle boundary help to understand core dynamics. Advances in computer technology have enabled us to take decisive steps forward in our understanding of the Earth's interior. Thanks to increasingly sophisticated numerical models, scientists can now accurately simulate processes taking place thousands of kilometers below the surface, where direct observation is impossible. These computer models combine several types of data to create a comprehensive dynamic representation of the Earth's internal structure. Seismic data are at the heart of this modeling. They reveal the variations in density and composition of the different layers as a function of the speed and behavior of seismic waves. This is complemented by the results of laboratory experiments, where extreme temperature and pressure conditions are recreated to study the properties of mantle and core materials. Gravitational and magnetic field analyses also provide essential information on mass distribution and motions within the outer core. Beyond simple static representation, computer models can simulate the dynamic processes at work in the Earth's depths. They reproduce, for example, convection currents in the mantle, responsible for plate tectonics, or geodynamo, the complex mechanism that generates the Earth's magnetic field. These simulations help us to better understand phenomena such as the planet's thermal evolution, magnetic inversions, and the impact of core-mantle interactions on tectonic movements. Computer modeling offers promising prospects, not only for fundamental research, but also for practical applications. For example, these models can be used to refine predictions of earthquakes and volcanic eruptions by identifying particularly sensitive zones. They also play a key role in the exploration of natural resources, such as mineral deposits or the exploitation of geothermal energy. These discoveries help us to understand crucial phenomena, such as the magnetic field that protects life on Earth from solar radiation and enables the existence of a breathable atmosphere, as well as gravity, which holds everything in place, from oceans to geological structures, and influences natural cycles such as tides. Magnetism and gravity are two of the many pieces of the puzzle that enable us to understand our planet. But what remains to be discovered? The Earth's mysteries are only just beginning to unfold. Our journey to the center of the Earth begins by crossing the first barrier, the Earth's crust. Compared to an apple, the Earth's crust is like its skin, extremely thin compared to the rest of the planet. Yet this surface layer contains the history of the Earth itself. The crust is not only the most accessible layer of our planet, but also the one best understood by scientists. The Earth's crust, although representing barely 1% of the Earth's total mass, is in perpetual evolution, shaped by the Earth's movements and internal energy. The result of dynamic geological forces, the Earth's crust is made up of solid rock and minerals. 3 types of rock make up this layer. Firstly, igneous rocks such as granite and basalt, formed by the cooling of magma, are the most widespread. Next come metamorphic rocks, transformed by pressure and temperature. Finally, sedimentary rocks, created by the accumulation of particles and sediments. With an average density of 2.7 grams per cubic centimeter, the crust is much less dense than the Earth's inner layers, which explains its relative buoyancy. It is divided into 2 main types. The first, the continental crust, is thicker and composed mainly of granite. This rock is rich in quartz and feldspar, the minerals that form the foundations of our mountains and continents. The second, the oceanic crust, is thinner but denser, dominated by basalt, a dark rock derived from underwater volcanic activity. Thin and young, oceanic crust extends beneath the vast basins of the oceans, with a slightly higher density, around 2.9 grams per cubic centimeter. The oceanic crust is an essential component of the Earth's lithosphere, extending from the Earth's surface to a depth of around 12 kilometers, or 8 miles. It is characterized by its stratified, uniform structure, particularly in deep ocean trenches. Oceanic crust can be classified into several geological entities, mainly ocean basins, mid-ocean ridges, and island arcs. Ocean basins are characterized by water depths exceeding 4 kilometers or 2.5 miles. Their structure is stratified, with 3 main layers. The first layer is less than 1 kilometer or 0.6 miles thick. It is made up of sediments of marine origin that have been deposited on the ocean floor over millions of years. These sediments include foraminiferal fillings, chert and mudstone, which bear witness to the conditions of the marine environment during their accumulation. The second layer, varying in thickness from 1 to 2 kilometers or 0.6 to 1.2 miles, consists of basalts and dolerites. These rocks, often present as pillow lavas, dikes, and sills, are the result of extrusive and intrusive volcanic activity. They are among the main rocks forming the oceanic crust. The third layer is the thickest, ranging from 3 to 5.7 kilometers, or 2 to 3.5 miles, and constitutes the true crust. It consists mainly of dolerite, gabbro, and amphibolite, mafic intrusive rocks that result from the slow crystallization of magma beneath the surface of the crust. Occasionally another layer is present, up to 3 kilometers or 2 miles thick. It is composed of metagabbros and pyroxenites, types of mafic and ultramafic intrusive rocks, underlining the geological complexity of the oceanic crust. Mid-ocean ridges like the Mid-Atlantic Ridge have distinct geological characteristics compared to basins. In these zones, the first layer is often absent, while the second layer, thicker than normal, outcrops at the surface. The third layer, on the other hand, is generally thinner and transits directly into the upper mantle, reflecting the geodynamic activities that define these tectonic parameters. Island arcs, such as those in the Indonesian arc, show a complex geological structure. The composition of the crust in these regions varies considerably, the result of a tumultuous tectonic history. Surface outcrops are dominated by volcanic andesites, typical of explosive volcanoes, as well as marine sediments that bear witness to a dynamic subduction environment, where tectonic plates clash. But how is oceanic crust formed? It all starts at the mid-ocean ridges, those immense submarine mountain ranges. Here, tectonic plates slowly pull apart, creating a gap that magma from the depths fills. When it comes into contact with the cold water of the seabed, it instantly solidifies, giving rise to new crust. This continuous process, known as seafloor spreading, means that the oceanic crust is constantly being renewed. This explains why it remains relatively young, with an average age of no more than 200 million years, a fraction of the Earth's age. Compared to continental crust, you could say it's still in its prime. Now let's turn to the continental crust, which forms the continents. Thicker, older, and considerably less dense, it's quite different from its oceanic counterpart. With an average thickness of 40 kilometers, or 25 miles, continental crust can reach up to 70 kilometers, or 43 miles in mountainous regions like the Himalayas. Its composition is dominated by granite, a light-colored rock rich in silica. This lightness enables the continental crust to float above the Earth's mantle. But what makes the continental crust truly exceptional is its age. Portions of it date back over 4 billion years, preserving fragments from the very earliest ages of the Earth. Unlike oceanic crust, continental crust is not easily recycled. It resists subduction, the process whereby one tectonic plate slides beneath another, and thus remains on the surface, bearing witness to the geological events that shaped our world. Although different, these two types of crust work in harmony to shape our planet. The Earth's crust is in constant transformation thanks to plate tectonics, a mechanism that creates and destroys the materials in this upper layer. Crustal plates are constantly moving, colliding with immense force and sometimes separating, resulting in mountains, earthquakes, and molten volcanoes. By studying these complex interactions, scientists are deciphering the Earth's history from its formation to modern times. The Earth's crust is much more than just a layer. It is the silent witness to billions of years of upheavals, creations, transformations, and the evolution of ecosystems. continental crust is rich in silicon and aluminum, giving it a lower density and a light color, often associated with rocks such as granite. Oceanic crust, on the other hand, is dominated by iron and magnesium, giving it a higher density and a darker hue, typical of the basalts that make up the seabed. This fundamental difference explains why the less dense continents literally float on the mantle and rise above sea level, while the oceanic crust sinks to form the ocean basins. The Earth's crust is also the scene of colossal forces that shape the surface of our world. One of the most fascinating processes is plate tectonics. Imagine the pieces of a gigantic moving jigsaw puzzle shifting, colliding, and sometimes pulling apart. These movements are behind imposing mountains like the Himalayas, active volcanoes like Etna, and the earthquakes that sometimes violently shake our cities and our lives. The theory of plate tectonics has made it possible to solve long-standing scientific enigmas. Why are marine fossils found on mountaintops? How can we explain the drift of continents, once grouped together in a superstructure called Pangaea? These plates, which move a few centimeters a year, also influence the distribution of rocks, minerals, and even essential natural resources, such as oil and gas. Crossing the Earth's crust is only the beginning of our expedition to the center of the Earth, but it already poses an immense challenge. Every rock, every hazard, and every technology used brings us a step closer to understanding the mysteries hidden beneath our feet. In the next phase, we enter an even more fascinating and little-known region, the Earth's mantle. Beneath the Earth's thin crust lies a massive and fascinating layer, the mantle. Located between the Earth's superheated core and its thin outer crust, the mantle is one of our planet's most fascinating layers. With an impressive thickness of around 2,900 kilometers or 1,800 miles, the mantle is a little-known realm where extreme conditions of temperature and pressure prevail, but which plays a vital role in Earth's dynamics. It accounts for 84% of the Earth's volume and 67% of its mass, making it the largest internal structure on Earth. The mantle is often perceived as a solid structure. However, under intense pressure and heat, its rocks adopt a plastic behavior, allowing them to flow very slowly over millions of years. It is this imperceptible movement that fuels spectacular surface phenomena, such as continental drift, volcanic activity, and even earthquakes. At the heart of the mantle, temperatures that can reach up to 4,000 degrees Celsius or 7,200 degrees Fahrenheit release colossal energy, essential to the Earth's geological cycle. By exploring this mysterious layer, scientists seek to unlock the secrets of our planet's evolution and how it continues to transform itself. The Earth's mantle, the intermediate layer between the crust and the core, is a world of contrasts and complexity. It is clearly distinct from the Earth's crust, whose composition is dominated by lighter granitic rocks. Mainly made up of silicates such as olivine, garnet, and pyroxene, the mantle also contains magnesium oxides and other elements such as iron, aluminum, calcium, sodium, and potassium. This mineral wealth is essential to the thermal and dynamic processes that regulate the Earth's internal activity. But what makes the mantle so fascinating is its non-uniform structure. It can be divided into two main parts, the upper mantle and the lower mantle. The upper mantle begins just below the crust at the famous Mohorovičić discontinuity or MOHO, and extends to a depth of around 660 kilometers or 400 miles. This boundary is characterized by a density contrast. The less dense crust gives way to the denser mantle, where seismic waves gain in speed. The average density of the mantle is 3.9 grams per cubic centimeter, well above that of the crust. The plastic part of the upper mantle is known as the asthenosphere, while the two solid layers above it, the upper mantle and the Earth's crust, together constitute the lithosphere. The lithosphere and asthenosphere, although distinct, are interconnected layers of the upper mantle that play a key role in the tectonic processes shaping the Earth's surface. Their complex interaction is essential to understanding the mechanisms of plate tectonics, the driving force behind our planet's geological transformations. The lithosphere is the Earth's solid outer layer, encompassing the crust in the upper part of the mantle, just above the asthenosphere. It is the coldest and most rigid of all the planet's layers, forming a kind of protective shell. Its thickness varies considerably. On average, it measures 100 kilometers or 60 miles, but can reach up to 300 kilometers or 190 miles beneath orogenic mountains, while it drops to less than 50 kilometers or 30 miles beneath the oceans. The lithosphere is not a uniform block. It is made up of large, rigid plates called lithospheric plates or tectonic plates, which float on the asthenosphere, a more malleable layer. These plates move slowly, interacting with each other along their boundaries. It is at these boundaries that major tectonic phenomena occur. For example, their collision can lead to the formation of mountains such as the Himalayas, while their separation promotes the creation of ocean basins. Plate interactions also generate intense volcanic and seismic activity, continually influencing the Earth's topography. Located beneath the lithosphere, the asthenosphere is an essential layer of the Earth that plays a key role in the movement of tectonic plates. This region of the upper mantle, which lies between the lower mantle and the lithosphere, and is often referred to as the low velocity zone, is distinguished by its unique properties. It is warm, soft, mechanically weak, and semi-viscous. This weak, ductile mechanical structure allows the lithosphere to slide and move over it, fueling the movement of tectonic plates. The particular viscosity of the asthenosphere, due to the partial melting of rocks, plays a fundamental role in the Earth's internal dynamics, facilitating the mantle convection processes that influence tectonics. Under the effect of intense pressure and heat, the rocks of the asthenosphere flow very slowly, adopting a highly viscous consistency comparable to that of melted caramel. With an average thickness of 200 kilometers or 125 miles, the asthenosphere lies at a depth of around 100 kilometers or 60 miles below the surface, extending as far as 650 kilometers or 400 miles. Unlike the rigid lithosphere, due to the high temperatures and pressures prevailing at these depths, the asthenosphere is composed of semi-molten rocks, mainly peridotite, rich in minerals such as olivine and pyroxene. This composition enables the lithosphere to float and move above it. The ductility and semi-viscosity of the asthenosphere make it a kind of conveyor belt for tectonic plates. It is thanks to this layer that the lithospheric plates can move, triggering geological phenomena such as earthquakes, volcanic eruptions, and continental drift. Together, the lithosphere and asthenosphere form a dynamic system in which the interplay between rigidity and plasticity lies at the heart of the Earth's geological evolution. While the lithosphere forms the rigid foundation on which life is based, the asthenosphere acts as a fluid transition zone, enabling tectonic movements. The interaction between the rigid lithosphere and the plastic asthenosphere is at the heart of plate tectonics, the process that continuously shapes the Earth's surface. The plasticity of the asthenosphere allows lithospheric plates to slide and move, while the rigidity of the lithosphere exerts a pressure that influences convection currents in the asthenosphere. These dynamics between lithosphere and asthenosphere have a profound impact on geological phenomena. When lithospheric plates collide, they can give rise to large mountain ranges such as the Alps or the Himalayas. Conversely, the process of subduction, where an oceanic plate slides beneath the continental plate, forms deep ocean trenches and volcanic arcs, such as those seen in the Pacific Ring of Fire. Earthquakes are also a direct consequence of this interaction. They occur mainly along lithospheric plate boundaries, where accumulated stresses are released in the form of violent vibrations. Likewise, volcanic activity is often linked to these subduction and divergence zones, witness to constant plate movements. There is a transition zone located between 410 and 660 kilometers, or 250 and 410 miles deep, which separates the upper mantle from the lower mantle. This water-rich zone contains crystals with a quantity of water equivalent to that of all the Earth's oceans. Further down, the lower mantle, the layer between the outer core and the asthenosphere, some 2,900 kilometers or 1,800 miles deep, is subject to colossal pressures. It accounts for 55% of the Earth's volume and is subject to pressures ranging from 237,000 atmospheres to 1.3 million atmospheres towards the outer core. This makes its rocks more rigid despite extreme temperatures, creating a stable but essential layer for heat transfer from deep within the Earth. Denser and hotter than the upper mantle, it forms a barrier to the exchange of matter. According to experts, diamonds form in the Earth's mantle at a depth of 150 to 200 kilometers, or 90 to 125 miles below the surface. They are transported to the surface by magma, which is brought up from the depths by tectonic processes such as plate divergence. At the base of the lower mantle, and around 2,700 kilometers, or 1,700 miles, a new denser layer of iron and silicates accumulates, known as the D double prime zone, slowing wave propagation. Close to the outer core, it varies in thickness from zone to zone. This layer, located at the lower limit of the mantle, marks the arrival point of oceanic plates that have plunged during subduction and is responsible for the plumes associated with hotspots. Convection currents in the Earth's mantle play a central role in the movement of tectonic plates, influencing the dynamics of the Earth's surface. This phenomenon is fueled by heat from the Earth's core, combined with the decay of radioactive elements in the mantle. As mantle material heats up, it becomes less dense and slowly rises towards the surface. As it nears the Earth's crust, this material cools and becomes denser, causing it to sink back down to the depths of the mantle. This process creates a continuous cycle, a circular movement that acts like a giant conveyor belt. Convection currents, though invisible, are therefore essential to understanding the planet's dynamics and the evolution of its surface. When hot magma from the mantle rises to the surface, it causes plates to diverge, creating mid-ocean ridges. These ridges are zones where magma solidifies to form new oceanic crusts, contributing to the expansion of the seabed. Subduction zones, where one tectonic plate plunges beneath another, bear witness to the dynamic interaction between crust and mantle. Here, crustal material is pushed to the depths, where it is partially melted and reintegrated into the mantle, once again feeding the convection cycle. These interactions between mantle and crust are at the origin of major geological phenomena, such as mountain building, the formation of ocean basins, and volcanic activity. Convection currents are therefore not only responsible for plate movement, but also for the geological processes that constantly shape our planet. The Earth's mantle also plays a key role in volcanic activity, notably through mantle plumes. These upwellings of abnormally hot rock from the deep mantle create what are known as hotspots. Unlike subduction zones or oceanic ridges, hotspots remain fixed in the mantle, while tectonic plates move slowly over them. This phenomenon gives rise to volcanic island chains, such as the famous Hawaiian Islands. As the tectonic plate moves over the hotspot, the intense heat of the plume melts the Earth's crust, creating volcanoes. When a plate moves over a hotspot, it allows the successive formation of volcanic islands, giving rise to an archipelago. This process is not only important for the creation of new land masses, but also provides valuable clues to the dynamics of the Earth's mantle. Hotspot activity gives us a better understanding of heat transfer processes within the Earth's interior, which influence mantle behavior and heat circulation on a planetary scale. Our understanding of the Earth's mantle has been greatly enriched by the study of seismic waves generated during earthquakes. These waves propagate through the different layers of the Earth, and depending on their speed and direction, offer crucial clues to the composition and internal structure of the mantle. Seismic waves can be bent, reflected, or absorbed by the materials they encounter, enabling scientists to deduce the properties of different mantle layers. A striking example of these discoveries is the observation of changes in the speed of seismic waves at different depths. These variations have made it possible to clearly delineate the boundary between the upper and lower mantles. This distinction is important as it reflects significant differences in the composition and temperature of materials at these levels. The movements of the Earth's mantle exert a considerable influence on the Earth's surface environment, which has direct repercussions on life, causing climatic and ecological variations that influence the evolution of species. For example, the opening or closing of sea passages can alter ocean currents and global climate cycles, resulting in periods of warming or cooling. These climatic changes have shaped the evolution of flora and fauna, favoring certain species while pushing others towards extinction. Mantle movements have also contributed to the formation of large mountain ranges and ocean basins, modifying the living and migratory zones of species. The mantle influences the distribution of natural resources, internal heat flows, and even climate cycles on a planetary scale. Consequently, understanding the Earth's mantle goes far beyond the study of the Earth's structure. It means understanding the global processes that sustain life and continue to dynamically shape our world. But that's not all. The mantle, although very powerful, is fed by an even deeper source, the Earth's core. This is where the ultimate heat is found, fueling the mantle's convection and ensuring the planet's dynamics. At the heart of our planet lies the core, a region as enigmatic as it is essential to the Earth's many geophysical phenomena. This extremely hot and dense structure, which extends from the submantle to the center of the Earth, is divided into two distinct parts, the outer core and the inner core. This metallic core is separated from the mantle by the Gutenberg discontinuity, which marks the end of the mantle and the beginning of the liquid outer core. Although this deepest layer is inaccessible to direct observation, it remains of vital importance for understanding the inner workings of our planet. Representing 33% of the Earth's mass and 16% of its volume, the core is a massive structure. Unlike the mineral-rich outer layers, it is made up mainly of iron and nickel. It also contains siderophiles, elements that dissolve in iron, such as gold, platinum, and cobalt. The core also contains much of the Earth's sulfur, as well as traces of oxygen and silicon. Metallic composition is essential for the processes taking place inside the Earth. The outer core, which measures around 2,200 kilometers, or 1,400 miles thick, is liquid and made up of molten iron and nickel. As such, it is responsible for the Earth's magnetic field through its convection movements. As for the inner core, it has a radius of around 1,220 kilometers, or 760 miles. Composed mainly of iron, it is solid, largely due to the extreme temperature and pressure conditions that prevail. Despite a temperature comparable to that of the Sun's surface, its presence of around 3.6 million atmospheres is sufficient to keep the inner core solid. The boundary between these two zones is known as the Lehman or Bullen discontinuity. The importance of the core in the Earth's geophysical phenomena is not limited to its composition. It also plays a key role in generating the Earth's magnetic field. The movement of liquid materials in the outer core, coupled with the effects of convection and the Earth's rotational movements, generate the magnetic field that protects the planet from solar radiation and plays a crucial role in navigation. The core also influences other geophysical processes, such as volcanic activity and earthquakes, by interacting with the Earth's mantle and crust. Studies of the Earth's core, although limited by the difficulty of access, provide a better understanding not only of the Earth's internal structure, but also of the dynamic processes that govern its evolution and ensure its geophysical equilibrium. Let's explore both parts of the core together. Did you know that the survival of life on Earth depends on a metallic core, hidden more than 2,900 kilometers, or 1,800 miles beneath our feet? The Earth's outer core, 2,200 kilometers, or 1,400 miles thick, is made up of iron and nickel in a liquid state. This layer, located beneath the Earth's crust, reaches temperatures comparable to those of the Sun's surface, around 6,000 degrees Celsius, or 10,800 degrees Fahrenheit, particularly at the Bullen discontinuity. Despite its extreme heat, the molten metal has a low viscosity, allowing slow convection movements. These movements, combined with electrical currents, generate the Earth's magnetic field through the self-exciting dynamo mechanism. This process, known as geodynamo, is a veritable dance of energy. When the liquid iron core of the outer core moves under the effect of convection currents and the planet's rotation, it generates electric currents. These currents interact with the Earth's rotation to produce a powerful magnetic field that extends far beyond our atmosphere, forming what is known as the magnetosphere. But why is this magnetic field so important? This magnetic shield deflects the dangerous solar radiation and cosmic rays that bombard our planet. Without it, the Earth's atmosphere could be swept away, leaving it vulnerable, like Mars, to lethal exposure. So the outer core is much more than a hidden metallic layer. It's a key player in sustaining life as we know it. At the center of our planet lies a fascinating and little-known structure, the solid inner core. The Earth's inner core, located at a depth of between 5,150 kilometers and 6,370 kilometers, or between 3,200 and 4,000 miles, is a solid sphere composed mainly of iron and nickel. Discovered in 1936 through the analysis of seismic waves, this core is a veritable time capsule, holding secrets about the Earth's history and thermal evolution. These vibrations generated by earthquakes travel the length and breadth of our planet. As they travel through the different layers of the Earth, these waves change speed, bend, or reflect, revealing the composition and state of the materials they pass through. P waves travel through solids and liquids alike. They tell us that the inner core is solid, as they can pass through it unhindered. S-waves, on the other hand, only travel through solids. Their inability to penetrate the outer core confirms that this layer is fluid. The main sources of heat in the inner core are the decay of radioactive elements such as uranium, thorium, and potassium in the Earth's crust and mantle, residual heat from the planet's formation, and the energy released during solidification of the outer core. Despite temperatures exceeding the melting point of iron, it remains solid due to the immense pressure and density it exerts. This core rotates slightly faster than the rest of the planet, creating a unique dynamic. The Earth's interior cools progressively over time. As it cools, the liquid outer core crystallizes and becomes part of the solid inner core. Remarkably, the inner core grows by about 1 millimeter every year, equivalent to the solidification of 8,000 tons of molten iron every second. As the surrounding liquid outer core loses heat, a thin layer solidifies on the surface of the inner core, like an ice cube growing in water. But this growth is not uniform. Some regions grow faster than others, creating a complex internal structure that intrigues scientists. This process has a direct influence on the Earth's thermal and magnetic evolution. Studying the inner core is essential to understanding how our planet has evolved since its formation. It also sheds light on the thermal processes that drive the geodynamo responsible for the Earth's magnetic field. The magnetism inside the Earth's core is around 50 times stronger than at the surface. The core's most obvious role is to generate the Earth's magnetic field, an invisible but indispensable shield. This field protects the Earth from solar wind, the streams of charged particles emitted by the sun, which could erode the atmosphere and make life impossible. It is also essential for human and animal navigation, guiding the compasses and migrations of many species. The heat of the core, meanwhile, fuels convection movements in the mantle just above. The Earth's inner core rotates in the same direction as the planet's surface, but at a slightly higher speed, making an additional rotation every 1,000 years or so. Within a few billion years, the Earth's core will solidify, and the planet's magnetic field will disappear. The Earth's interior, with its extreme conditions and incessant transformations, embodies the power and dynamics of our world, reminding us just how much our planet is alive and constantly evolving.